We saw reaction mechanisms in organic chemistry. We need to revisit this subject now and talk about reaction mechanisms in terms of rate laws. We know that a reaction mechanism is a sequence of events that describes the actual process by which reactants become products. This could occur all at once through one step, or could occur through several discrete steps. Each of these steps is known as an elementary reaction or an elementary process. Remember that we can't deduce a rate law from the overall balanced chemical equation, but we can deduce a rate law from an elementary reaction based on its molecularity. What is molecularity then? Molecularity of a process tells us how many molecules are involved in the process. Something that is unimolecular means that one molecule is reacting to form products. If we were to write a rate law for this, it would just be dependent on the concentration of A. Bimolecular reactions can happen a couple of ways. We could have a molecule of A reacting with a molecule of A. A rate law for this would be that the rate is dependent on A squared. Or we could have A reacting with a different molecule B, and then its rate law would be dependent on both the concentrations of A and B. So the rate law then is for an elementary step is written directly from that step. One example then for a one-step mechanism, this first one, Ag plus I minus, reacts to give AgI solid, happens in a single step. The rate for a single step mechanism is just going to be dependent on the reactants. A rate law expression for this example then would just be the concentration of Ag plus times the concentration of I minus. Another example, and this is where IB likes to link back to organic chemistry again, is our SN2 mechanism. Remember that this happens in one step. And this is a primary halogenoalkane. So let's just use this one here. Plus a sodium hydroxide, we'll write an OH minus, and that gives us our primary alcohol plus a Br minus. Because this reaction happens in one step, we can write a rate law expression for an SN2 reaction. That is going to be dependent on both the concentration of our primary halogenoalkane and our nucleophile. In this reaction, it's OH minus. Things get a little bit more complicated when we talk about multi-step mechanisms. In a multi-step process, one of the steps will be slower than all the others. The overall reaction cannot occur faster than the slowest step, which is termed the rate determining step. This is kind of like if you're driving and you're going through a couple of toll booths. Not that we have toll booths here in Canada, but we can pretend we do. Say, for example, the cars get slowed down at this first plaza here. Then the rate determining step depends on how quickly they get through Plaza A, because once they get through Plaza A, getting through Plaza B is really, really quick. Versus, in the second example, plaza A is relatively fast to get through, but then plaza B gets slowed up here. So in this scenario, plaza B would be the rate determining step. Figuring out the rate law for a multi-step reaction then requires a few extra steps and things we need to think about. The rate of a multi-step mechanism is going to be dependent on the rate determining step. In this example here, it's asking us for the rate law for this reaction, given that it occurs by this mechanism here. What you want to do is look for the step that is rate determining, and then you're going to base your rate law based on this step alone, because the other steps don't matter, they will happen quickly. The rate expression for this reaction then is going to be dependent on the HBr concentration and on the O2 concentration. It's pretty easy then if the rate determining step is the first step, because it looks very similar to those one-step mechanisms that we previously figured out. It gets more complicated when our rate determining step is either the second or third step. So in this example, what is the rate law of this reaction given that the mechanism occurs over these two steps? Again, we're looking for a rate determining step, which is now step 2. If we were to write a rate law, the rate would equal to the concentration of NOBr2 times the concentration of NO. But if we look at our reaction, the concentration of NOBr2, this is an intermediate, and it's going to depend on the concentrations of Br and the concentration of NO, because we need to react NO and Br2 to make NOBr2 in the first place. So these two reactants are also going to be part of our rate determining, our rate expression. What we want to do then is, where we've got NOBr2, we're going to substitute in NO and Br2. Because the concentration of NOBr2 is dependent on the concentrations of NO and Br2. We're then going to simplify it. So the rate expression for this mechanism is going to be NO squared times Br2.